A4, very similar problem. In a way, right? It's ionization energy problem. And so here, right, I gave you the first ionization energies, right? This is for the second row. So if, right, as I had mentioned when I was talking about B11, right, if I'd given you the first ionization energy, you could easily look at this chart and be like, oh, well, which one has, an ionization energy for the first one that's around 1,000 kilojoules per mole, right? You could have looked here and be like, oh, it's sulfur, and you wouldn't have had to go through all that trouble that we did, in the last one. But yeah, but here, right? So in terms of the problem, right? So we're given that trend. It says define first ionization energy, right? That's just something that you can, essentially look up. But what the definition is the amount of energy required to remove, the first electron from a neutral, atom, right? So going from, if we're talking about it, from a chemical equation standpoint, right? It's just simply, this process right here, right? Where you're going from X, element X to forming, X plus ion plus a free electron in that case. And so then part B, right? It says explain why the first ionization energy increases across the period, right? So that has to do with the fact that essentially the effective nuclear charge is increasing on each one of those elements, because as you're, even though you're adding both a proton and an electron for each one of those atoms, right, as you're moving across, the electrons that are being added aren't doing a great job of shielding, the new electrons, so to say, that are being added in those cases. And so, even though you're getting now a full plus charge, right, you're not really, completely negating that, how much of that plus charge those electrons are feeling in those cases, right? So the Z effective isn't, increasing the same, like linearly, or not linearly, isn't increasing the same amount across them, right? And so because of that, the electrons that are being added, with each proton are feeling, more and more of that proton. And so that's, pulling on those electrons more and making it more difficult to have those, electrons be removed, in the ionization process. Right. So it comes back to Z effective, essentially, and how much shielding the electrons that are in the same, end level have with each other. Part C, there's a break in the trend between magnesium and aluminum. Explain why the first ionization energy of aluminum is less than that of magnesium. So that has to do with thinking about orbital filling, right? Because if we look at both of those, right? So if we look at magnesium, right, the electronic configuration that we have for magnesium is, right, the noble gas configuration of neon, and then 3s2, right? And so then magnesium plus would have the electronic configuration of 3s1, right? Because we're now going to be taking one electron out of that system in that case. And so then in the case of aluminum, right, what we have is the electronic configuration of 3s2, 3p1, and then Al plus is 3s2 in that case, right? So what's happening is that, in the case of the magnesium, right, when you take that one electron out, what you're doing is you're breaking up a fully filled orbital, right? So there's a stabilizing effect that comes with fully filling the orbitals or half filling the orbitals, because they're interacting and everything like that with each other. And so if you're taking one electron out of the 3s2, right, and you're forming the 3s1, right, we're going from a fully filled orbital now to a half filled one, which isn't, as stabilizing necessarily. Whereas in the case of the aluminum, right, what we're going from is 3s2, 3p1. So we have just one electron hanging out in the 3p all by itself. And then now, right, when we take that one electron out, we end up with, a filled 3s orbital as the only orbital that we have left. And so because that 3p is further out compared to the 3s, right, because, it's a higher energy orbital, you can expect it to be able to be pulled off a lot easier compared to the 3s, right, in the case of the magnesium. And then also, right, when the case of the aluminum plus, right, now we have a fully filled orbital configuration. So that's, a favorable interaction in that case. And that's why you see that slight dip in ionization energy between magnesium and aluminum, right, for that first ionization energy. Part D, phosphorus and sulfur, right? Same exact type of trend in general, right? So in the case of phosphorus, what we have is neon 3s2 3p3, right? And then in the case of sulfur, we have neon 3s2 3p4, right? And so then P plus is 3s2 3p2, and then sulfur plus forms 3s2 3p3, right? So in those cases right there, right, if we draw out what the orbital filling is for phosphorus, right? So in the case of phosphorus, what we have is, you know, this configuration right here, whereas in the case of sulfur, what we have is this configuration right here. And so when we pull out an electron from the p orbital, right, we or not p orbital, sorry, from phosphorus, right, we have a full set of half-filled orbitals. Taking one of those electrons out, right, is not that favorable, because, right, having a half-filled orbital set is more stabilizing than just simply having extra ones, right? It would much rather have those. If you ever take, like, Chem 500 or something like that, and Professor Rumsey may have talked about this as well, right? But there's such a thing as called exchange energy that happens, where the different electrons, right? If you have electrons that are in degenerate orbitals, they all have the same spin, right? They can actually, exchange with each other, and that actually has a stabilizing effect. And so in the case of, phosphorus, right, there's 3 of them, and so, those can all exchange with each other, so that stabilizes it. If you take out one of those electrons, now you only have 2, so there's only 2 that those can stabilize and exchange with each other. And so, you're kind of, impacting that a little bit. Whereas in the case of sulfur, you have essentially one fully filled p orbital, but you then have 2 half-filled ones in those cases. And so if you're taking that one electron out of, the fully filled p orbital, you're removing a bit of a Coulombic repulsion that happens between those 2 electrons, right? Because we also have to think about the fact that when we have 2 electrons in an orbital, those 2 electrons, right, are both negatively charged, and they're occupying the same volume, and so they're going to have, some kind of, destabilizing effect where, they don't want to interact with each other, right? If you take 2 magnets and you put the 2, negative pole parts together and you push them together, right, they're going to push back, and stuff. And so, that happens with electrons as well, because they're both negatively charged. And so if you take that one out, right, then, you kind of, provide a little bit of relief to that electron, in that case. And so that's why you see that dip, right, where it doesn't take as much energy to take out that first electron in the case of sulfur compared to the phosphorus, right? And that's why it has to do, right, is that because you're going to a half-filled orbital configuration for S plus, right, which has a bit of a stabilizing effect in that case, and you don't have that repulsion anymore, versus, in the case of phosphorus, you're taking one electron out, and then now, right, you're breaking up that half-filled orbital set that you have. And so that's, the reason why you see that dip there. And so it's the exact same trend that you see, if you go down the table, right, if you look at the second row, you're going to see that same trend where, you have, lithium, beryllium, and then you fall down and it has boron, and then carbon, nitrogen, and then nitrogen falls down to oxygen, right? Oxygen has a lower first ionization energy compared to nitrogen, which seems counterintuitive compared to everything that we know about oxygen, right? How oxygen wants to be, have a charge of 2- and everything like that. But that's, experimental fact, right? Is that you do see that dip, and it has to do with the fact that you're changing those things, right? And if you move down the periodic table and you start talking about selenium and arsenic, right? Same exact thing, right? Those trends stay the same, and it has to do with the fact that you're going from, those different types of electronic configurations and how that's impacting it. So that's A4.